Hello, everyone. Welcome to today's webinar hosted by Densify co-founder and CTO Andrew Hillier. I am Chuck Tatham. I'm the Chief Revenue Officer of Densify, and I am here to host the session. The topic is a very interesting one that Andrew spends a lot of time thinking deeply about, and that is effective management around larger scale or scaled Kubernetes environments. We see extensively repeating patterns with respect to the challenges enterprises are facing around managing Kubernetes. We're going to talk about some of those challenges, a lot of real data from the field, which is a great support to the conversation and the topic at hand. So I'm going to hand over to Andrew quickly, and he'll get to the content.
Thanks, Chuck, and thanks everyone for joining. The topic: 3 ways to optimize your clusters. I'm going to go through these 3 things in some detail. There'll be a bit of repetition because I think it's important to reinforce these things with actual data. And it all follows on, I think if you looked at prior webcasts, maybe a few months ago, we have a poster around the 12 risks in your Kubernetes environments. And they stem around there's CPU requests and CPU limits and memory requests and memory limits, and they can be too high and they can be too low. They can be not set at all. And some of these things create problems and some don't. And so what we found is that we've really seen over the course of doing a ton of analysis in customers, it really distills down to 3 big problems we're seeing. There are other ones, but we want to focus on these 3 and let me get right into them. So the common issues. And this is the big one. This usually starts conversation. It aligns with a FinOps mandate that the environment's too expensive. There's unnecessary spend. It's usually due to over provisioning of the containers. It could be also because you have inefficient scaling and some other things, but I'm going to focus on the containers. If you make the containers too big, then they use up a lot of capacity. They run on a lot of capacity and they don't use it, and they strand a lot of capacity. I'm going to cover that in some detail. So if you're a FinOps practitioner or related to that at all, this is important because there's usually some very straightforward ways to cut this out. On the other hand, we also see containers getting killed, and there's 2 reasons for this, and we're refining this all the time. If you land on a node that's, for example, out of memory, you might get killed. You might have a hard time. I'll show some examples of that. But also, even if you're running on a healthy node, you can get killed if your limit is wrong, especially your memory limit. You'll get throttled if your CPU limit is too low. But the memory limit, if you exceed it, you can actually get killed. So a lot of times we'll see all 3 of these happening in the same cluster, where some clusters we see they're just a bit of a mess. They're wasting a ton of money and things are getting killed. This lose, high risk, high cost situation. And not every cluster that's way, but an awful lot of them are. Pretty much every customer we see has clusters like that and has at least 1 or 2 of these problems going on in their clusters. So that's the problem statement. Let's drill down into why that is. And if we look right down the deepest level, when you start a container, or in this case, a pod with a couple of containers, you need to set these requests and limits for CPU and memory. And we've seen from the beginning, we figured this is probably hard to do. And we continue to see that it is extremely difficult. The whole webcast where I give the analogy, it's almost like trying to tell your laptop how many millicores Outlook needs and how many millicores PowerPoint needs and how many millicores Excel needs. Like, who knows? I use those things every day and I have no idea how many millicores I would give them. And so even if you're an expert in Kubernetes, this is very difficult because it's also, you might not have the data to see this. What if this is a highly replicated pod or a highly replicated container? What do I give it? And so we find even people that know Kubernetes well, and even people that are sitting at Grafana, it's still hard to set these things properly without the right analytics. And the patterns we see are things like this, where this is the CPU utilization of a container in millicores over 24 hours. So this is a pattern model of what that container does typically. And you see it's kind of hitting 750 millicores, like 3/4 of a CPU. But the yellow line at the top is the request. The purple line is the limit. In this case, the request is equal to the limit, which is probably a different issue for CPU. You would rather do that. But focusing on the yellow line, we've given this 2 CPUs, and it's not even using 1 CPU. And I'll talk about the implication of that in a second. So that's a big part of that first thing I mentioned around excessive cost. If you're over provisioning, we see it on memory too, but we see it a lot on CPU. This is just going to waste money. And I'll talk about that more in a second. On the memory, you see a case here, this container where we've given it 1 gigabyte, but it's using between 2 and 3. So again, I've given it not nearly enough memory in this case. I'll talk about that in detail too. So that's that second case. If I do this systemically, my nodes get overstacked and things get killed. And I'll show that. And the third one is this limit. If I make that limit too low and the workload actually hits that limit, particularly if the working set of the container hits that limit, bad things happen. And I'll talk about that as well. You can get process kills inside your container. And again, I'm going to show examples of all three of these things, but these are really the root cause at the lowest level of these kind of business problems where we have instability, we have cost. All of these can be traced back to, in many cases, to these settings being wrong, and they're very difficult to get right. So let's talk about these one by one. If I set the CPU request too high, then I'll give out all the resources of the nodes, but they won't actually be used. And here's an actual cluster. This is the aggregate requests values as a percentage of the capacity of a cluster. So the way you would read this is that the Kubernetes scheduler is giving out 80 to 90% of the resources of the cluster to containers, which is great. That's its job, is to continue to run. This says, I need two CPUs. Okay, you take those two, you take those two, and it gives them all out, and it moves on to a new node when it fills them up. But in this example, the actual utilization was average 7%, peaking at under 20. And this is extremely common. So we got very poor utilization of those resources. And oddly, we see this kind of quite a lot. Like, in fact, for a while, we were seeing kind of 7% in a lot of different environments, a weird coincidence. And it makes sense. And one of the reasons for this is because I think people have been used to virtual environments where you're giving out virtual CPUs and you can give them out more than once. So in a VMware environment, I could run an 8-to-1 overcommit where that's fine. I'm going to give you a CPU. You're not using it. I gave the same CPU to somebody else as well. And between you all, you're going to use it. And if I were doing that here, that 7% would actually be 56%, which is what you would see in a VMware environment. But containers don't work that way. When they're scheduling, when they give out the CPU resources on the node, they move on to a new node. At runtime, you can steal from each other. But when scheduling, it will not give out the same resources more than once. So what happens is this cluster will just sit there, or this node group will just sit there running at very low CPU utilization, stranding a lot of capacity, creating unnecessary costs. Again, we see this again and again, where just reining this in would let you run on a different type of node with fewer CPUs and save a lot of money. Again, moving from a general purpose to a memory optimized node usually saves about 30%. And you can do that, but not if you're giving away all these resources, because in this case, you need to have enough node resources to underpin the requests, even if they're not being used. So the left curve is what's going to dictate your spend, whether you're using it or not. So that's problem number one. And then again, obviously, if you eliminate this problem, you'll eliminate a lot of your costs. The second one, setting memory requests too low. So I mentioned things getting killed. So what happens is, let's just say, for argument's sake, I have a memory usage pattern that looks like, I know memory doesn't usually go up and down quite that much, but for argument's sake, let's just say it's that, and this is the Tetris representation of that workload. That could be by hour, it could be by day, it doesn't really matter. What happens is, if I schedule this onto a node, but I don't ask for enough resources, if it's peaking at 2 gig of memory, but I only ask for 1, Kubernetes says, okay, fine, I still got a lot of memory left on this node. I'm going to keep stacking these things on until it blows up the node, and you'll get another memory kill. So at the node level, when you saturate a node, something's going to get killed to alleviate the pressure. And if you systemically undersize things, then what happens is that the nodes, you get out of memory kills. It's that simple. The converse is also true, that if I have something that doesn't use much memory, but I ask for way too much, then Kubernetes says, well, okay, I only have so much space left. I'm going to put one more of those there, and I'm going to start a new node or move on to a new node. But in reality, that node is going to be very underutilized from a memory perspective. The same thing can happen with CPU, but we don't see it very often. We don't really see nodes hitting 100% for CPU. Usually they're way over allocated for CPU. But for memory, yep, you can have some nodes hitting 100%, some nodes sitting at 20%. And you can have them in the same node group, in the same cluster. So the folks of this, the big problem we see here is that the left-hand side, when they do overstack, you do have stability problems because things get killed. The reality is you also have a lot of nodes that are not well utilized, and you could be wasting a lot of money at the same time. You could have a node group that's only half utilized, but some of the nodes are hitting 100%, and so you're wasting money and you have high risk. And I'll show examples of this in a second. The third problem, setting memory limits too low. This one's a little more straightforward, but it's a little more nasty as well. So here's a case of a container. This is the memory utilization metric. And again, the orange line or the yellowish line is the request. The purple line is the limit. And you can see it's tapping the limit. Every hour, it's tapping the limit. And the green curve, the right-hand one, is what we're recommending. We're saying get that limit up. Don't keep it that low. You're going to hurt your workload. And again, so this tapping of that limit, I'll say it might cause problems. It might not. In this case, that thing's got a lot of restarts. So that container was restarting quite a bit. Again, sustained restart activity all the time. So this is not a healthy container. It could be on a node that has a ton of capacity. Your cluster might be beautiful from an overall capacity perspective, but if you misconfigure this, then you can cause localized issues with that pod or that container. And so to give a bunch of disclaimers here, when we see this, we say, well, it might not be an issue. If your app is architected well, then a cloud native app, microservices, if they restart, it might be fine infrequently. Usually people don't want it happening at all, but you might start with it. But this kind of sustained restarting is rarely good. Again, depending on the app, it could back up the queues. It could cause user experience problems, all kinds of stuff. So when there's this level of restart activity, that's not usually a good thing. It is possible to hit the limit and not have restarts. We've seen this as well, but if you see this pattern and this workload has a lot of memory caching, a lot of buffering, then hitting the limit will just kill off the buffers. And so it will affect performance, but you won't die. So you can see this pattern happening without restarts, and the thing might be running fine, or it might be behaving a bit, slowing down a bit because it's not caching as much anymore. So again, there's all kinds of things that happen when you go this. The trick is to get to the bottom of it. If the working set hits the limit, then you've got an issue. And this last point I'll make, which is possibly the worst, and I'll show an example of this. If you hit the limit, it's not a memory kill from Kubernetes, it's the Linux kernel that's killing a process inside your container. And if it kills process ID 1, then you get a restart because your container will just restart and keep going, which is nice because then your container can come back up in a healthy way. If process ID 1 isn't the one that's killed, if it's a fork process, then you won't get a restart. The thing just keeps running in some degraded state. And that's probably the most evil one. And we do see this almost everywhere where some container is running along, missing a process. Who knows what process? It could be the hourly data load. It could be, who knows? And again, it's one of the things we're seeing this is it can lead to zombie pods that are sitting there not really doing anything anymore because something inside them got wrecked. And very few companies would architect a container to survive a process kill inside the container. Usually you can architect it to restart the whole container, but not if you lose something inside the container. That's pretty tricky. So that's the memory limits too low. So I'm going to show some actual examples of this and just a quick word on what I'm going to show. So the way we approach this is we analyze the containers and analyze all the patterns of activity from the Prometheus node exporter data. And we basically learn the patterns of these workloads. And we've shown a bit of that already and understand what the peak and sustained activity is, all the replicas. We analyze all the replicas, understand the busiest versus the average replica. It may be that only the busiest replicas are hitting their limit, the other ones aren't, which is even harder to find. So the usage patterns, the replication patterns, very deep policies around how you want this to behave. Do you want it to, are you trying to size very conservatively or are you trying to be more aggressive? And the result is very specific recommendations on how to set the requests and limits, as well as a visualization, which I'll show because it's almost like an MRI for your container environment. From this, you can glance at it and say, okay, I see what's going on here. I've got this problem or I have that problem. And you can do that across tens of thousands of containers. You can do it across your whole company if you want to. You can visualize it. So very specific recommendations plus a visual to help you understand thousands and thousands of recommendations all at once. And of course, you can get all this through the API, there's the UI. We have Terraform integration. I'll cover some of that towards the end. So on the recommendation front, this is what, if you pull up the UI and drill down into it, you're going to see something that looks like this. These are a bunch of containers with what namespace they're in, the controller type, and all these things. And you see there's a whole variety of optimization recommendations. And containers are more complicated than, for example, cloud environment because you can have multiple things going on at once. Like at the very bottom of the list is an upside. That's pretty straightforward. It needs to be made bigger across the board. Or a downsize is too big. We need to make everything smaller. Request the limits, everything. There's resize where you're wrong in multiple directions. Like that first row is too big for the CPU request and too low for the limit. And that's actually the example highlighted at the bottom here. We also have size from unspecified. So we see cases where you don't have a value. It may be okay in the kube system namespace. These aren't in the kube system namespace. They should probably have a value. And that causes all kinds of problems as well. I did a whole webcast on the problem with unspecified values, going into detail about what will happen when you don't specify a value. So again, if you're interested in that, there's an entire webcast just on that topic of size from unspecified. But back to the top, this example is the one that's highlighted at the bottom here. In this case, we see the request is equal to the limit. It's 4 CPUs, and we're saying that maybe isn't optimal. In some cases, request equal to limit is the design point for guaranteed quality of service, but usually for memory. It rarely makes sense for CPU. In this case, we're going to throttle this thing as it goes above 4 CPUs, which it clearly does. And we're requesting 4 when most of the time we're barely using 3. In fact, most of the time we're using 1.5, less than 1.5 or 1. So the analytics based on policy is saying, okay, get the limit up out of the way so we're not throttling this thing. We see some customers not even setting CPU limits. That's another way to go. And bring the request down to closer to the sustained activity. That thick green line there is spending its sustained activity at that level and then peaking up above that. We don't need to request to the peak. That's very inefficient. We could probably even bring this down further if you want to, if the cluster is really healthy. But at the very least, just bring it down a bit. You're going to save some money and you're going to prevent throttling of CPU. So yeah, that's an example of a recommendation. And then all these kind of numbers, if you scroll to the right, there's all the numbers of exactly what the recommendations are. You can read them in the UI. People rarely want to read 10,000 rows of recommendations. So of course, it's all available through the API. And usually I'll show the way you integrate this and prioritize and integrate these recommendations a bit later on. So that's an example of the raw recommendations. We were working with one customer a while back and they said, that's great. Can I see this for an entire line of business or entire business group or namespace, or show me all my Istio proxies in my whole company? Are they okay? And so that's where we came up with this visual. And the way you read this is a 4-pack. We call it the 4-pack. So it's top left is CPU requests, top right is memory requests, CPU limit, and memory limit. And it's rendering all the, in this case, about just around 11,000 containers. Again, you can do as many as you want and any logical grouping of containers. Doing a cluster, typically looking at a cluster makes sense in a lot of cases, but you can look at anything you want. And the way you read this is that on the CPU, on these percentages, the green are the ones that are set correctly. The yellow at 500%, that's how many containers are 5 times bigger than they should be or more. The red at the left is the ones that are a fifth the size. So the percentages, we buckets of whether you're too big or too small. So in this case, the way we're reading this is that we've got a ton of containers that are over 5 times bigger than they should be from a CPU perspective. In fact, at the top right, you see there's a ton of CPU surplus in this environment. That's the cost savings opportunity. So that's, again, back to the 3 things. If you see this, number 1, that's the problem, the spend problem, and this is how you fixing this will fix the spend problem, or a lot of the spend problem. On the memory requests, in this case, almost 1,000 containers are a fifth the size they should be. They're way under spec. That creates that second thing I was talking about, where if they're all small, then your nodes will be exhausted. At the same time, though, thousands of them are also way too big. And we see this everywhere, where memory's wrong in both directions. In fact, in this particular example, there was almost the right amount of memory overall. It was just given out completely wrong. So there wasn't a lot of memory savings opportunity overall, but these yellow ones were helping the red ones survive, because if, back to those Tetris blocks, if you schedule one that's too big on the same node as one that's too small, they help each other. The one that's too small, the resources will be stolen by the one, or the one that's too big will give resource to the one that's too small. So you can limp along, but you're probably going to have problems. And I'll show exactly what those problems look like with this spread. A big gray bar is also bad here. If you're not giving requests, same thing. You're going to overstack the nodes. On the limit front, these red ones, although they're usually fewer, those are the evil ones. That's where you have things getting killed because they're hitting their limit, even if the rest of the environment is fine, even if all the nodes are fine. And that's that third problem. The gray bar here is a slightly different problem. That's not good either, except maybe in kube system. If you're not giving things limits, then processes can have a memory leak and take out a node. And we've seen that happen as well. Again, that's topic of a different webcast, is that the gray bars here. So again, 1, 2, 3, let's keep going here. I'm going to show some actual examples. Here's number 1. So this is a case where I've got some Tomcat containers that have been given 9 CPUs, 9,000 millicores, and are using, these first 2 are using about a tenth of a CPU. So they're just way too big. And so those resources are chewed up, and it's going to cause the node utilization to go down unnecessarily. There's the first one, there's 2 copies of the second one running. But this fourth one down, I want to focus on because it's got 9 CPUs as well, and it's using about 5 CPUs worth of capacity. So it's about 4 CPUs too big. And you can see the curves at the bottom. I don't need 9 CPUs for this workload. Even the busiest replica is only hitting 5 CPUs. So I can bring that yellow line down and save a ton of money. And the beauty is it's replicated 112 times. So some quick napkin math on this one. If that's racing about 455 CPUs of capacity, or almost $200,000 a year at list. So usually we find, this is a pretty extreme example, but usually we find there's kind of a big 80-20 rule here. Usually hitting the biggest egregious oversized containers or the highly replicated oversized containers can make progress very quickly in bringing down that yellow bar and then causing you to be able to run on pure CPUs and save money. Independent of memory. You don't have to touch memory. You can just move to a memory optimized node with pure CPUs and save if you can get a few of these bigger offenders down a bit. So that's the yellow. That would decrease the yellow bar we see here. That's the whole FinOps value prop, and that's one direction. The memory is there is savings, often savings opportunity, but the bigger one we see is the kill risk. So here's an example of a Kubernetes node group, a big node group with 72 workers, and this is the average and peak memory utilization of each node. And if you scan down this list, you can see it's all over the place: 18, 75, 99.3. And if we sort it, we see the top nodes, the busiest nodes, are all basically hitting 100%. You never see 100% in this list. 98, 99, 97 means you're in striking distance of running out of memory, and you probably have out of memory kills happening. So this top one, for example, you can see by hour of day, after 4 p.m., it's just whacking the ceiling all night. That's not a healthy pattern. That will cause memory kills. But in the same node group, the bottom node is chugging along at 15.8% utilization. So this is the lose here. We've got things, this environment did have a lot of out of memory kills happening on these, with things on these nodes, and it had a lot of wasted memory. The average, I don't know what the average was for this node group, but you almost half the memory was wasted, yet you still have kills happening. So this is that lose we see in almost every cluster. At least in every cluster, there'll be a node group doing this, because unless somebody has all the requests and limits set properly, this is going to happen. It's those Tetris blocks getting all jumbled up, and some nodes hitting the roof and some not. Third case, and I'm just watching the clock here, only a few minutes left. These red in the memory means that things could be hitting their memory limit. Here's an example of a container that's a pretty big container that's whacking its memory limit again and again. We're recommending to bring that limit up. And there was restart activity, pretty regular restart activity on this container. And that's, again, not a good thing. So that's the case I was talking about earlier. If you see this, especially in a highly replicated container, this could be a big problem. And the other one, which is, like I said, even more evil, in this case, this one's also hitting its limit, but there were no restarts. So this one is probably one of the worst. Like I said, this means that in all likelihood, a process is being killed inside this container. You see those little dips in the curve? That's probably the heap going down as the process gets killed and tries to restart. So that's not a healthy pattern. And if there's no restarts, it's probably you're running blind to it. You would never see this in any monitoring tool. We are actually in the process of adding a hidden kill metric, a derived metric on this to track when this is happening, when the working set hits the limit, and you likely had a process kill, because right now a lot of organizations are blind to it. And so again, that's a particularly important one. It may not be a ton of these, but we do see them in a lot of environments, including production environments with a lot of capacity. It doesn't matter if you have a lot of capacity or not. This could be happening to your container. So just to wrap this up, again, I'm just watching the clock to prevent this. Well, it's pretty straightforward. You find and fix these problems. So they analyze the CPU patterns, make sure things aren't wildly overspecified, so you can reduce the stranded CPU capacity, cut spend, analyze the node memory utilization, and look for hotspots and avoid imbalance across nodes, and start container and node utilization. So the node will show you the symptom that something's happening. The container memory utilization is how you get a better request value for memory, so that you're not having a problem. So if you fix the most undersized containers, usually the memory kills will go away because you're not overstacking the nodes anymore. And then you can go after the cost problem next. And then the CPU and memory patterns to make sure, of the container level, to make sure you're not having killing or throttling. Again, some customers have problems with throttling, but and that's bad, but the kills are worse. And oftentimes that might be the first one you go after, because it's very isolated. You can just fix those things pretty directly. So doing all this analysis, then you generate precise recommendations, prioritize them to make sure you understand which ones are going to make the most difference, and then do them. And so the last thing I'll talk about is implementing the recommendations. And there's numerous ways to do that. You usually don't want to go and hand type new values in every manifest. So I'll show an example of this. Right now I'm seeing screen sharing is paused. Oh, there he goes, going again. So this is an example. It's a case study that's on our website of a customer where every deploy, they do this analysis I've been describing, come up with all the ideal requests and limits, and then every deploy, they hit our API, get the values, and build them into the manifest, the template in this case, the OpenShift template, and deploy them into the wild. So every time something deploys, it's optimized. And this makes a ton of difference. So their histograms look like this, where mostly green. It's very good from an optimization perspective. The only reason there's still outliers here is because the policies don't make too big a change at once. You can set the policy to say don't take away 99% of my resources in one step. So things converge on the green. There's no gray, so very good hygiene. Nothing has an unset value. This is what good looks like. And these folks cut their new infrastructure spend in half by doing this because things were stacking better. The bin packing was better. Kubernetes just does a better job if you give it better inputs. And again, there's a link on our website to the case study. And the last thing I'll mention is VPA is another way to do this. Is one of our newer integrations where VPA has a recommender, but it's not, in our opinion, not very good. It doesn't look at the depth of the data with the policies that we do. So it might be able to upsize things if there's a problem, but it's not very good at reclaiming or saving money. But we can be a recommender. So we have an integration to be the recommender. So VPA can just dynamically override as they're deployed the settings and fix all these problems. And it's a nice way to go because you don't have to go back to 1,000 Terraform files or manifests in the app teams and change them all. It can just be done centrally to override them. So that's another way to drive automation of fixing these things. And with that, I won't cover this in any detail because we're a bit over time, but that's not, there's that type of integration. There's also a ton of other integrations that can be done to share shame back reports, put things in BI tools, open tickets if that's needed. A lot of times there may be change management around these things, sometimes not. So again, there's more information on this on our website, other ways you can tie this into the ecosystem. Last but not least, because of what I've shown, we are actually ranked a leader by GigaOM on their Kubernetes radar. So we're quite happy about that. I think we're about a millimeter ahead of the next one down, but so that's great for us. There's information if you scan this, you can see the report. The poster I referred to at the beginning, that's available as well. Those are all the different things that can go wrong if you have these settings too big, too small, not set. I focused on 3 of these areas, but there are actually more that's available as a poster. And we also have a podcast where we alternate between cloud and container topics. So there's a lot of good container and cloud information on our podcast. And with that, I will stop talking.
People have stayed on, so I'm just going to throw a couple questions that were posed, if you can answer them quickly versus leaving them unanswered. One is, does this, everything you've talked about here, fit for OpenShift?
Yeah, and I showed an example towards the end. So OpenShift works the very same way as far as the analytics. And if it's OpenShift in the cloud, then we would optimize the nodes the very same way. OpenShift on-prem is a bit different because it's often running in a VMware VM. So the node optimization obviously is a different strategy. But from the pure container and the histograms, in fact, some of the, I think probably half the examples shown in this deck might have been OpenShift environments. It's the very same problem.
You mentioned nodes in your comment there. Comment on node optimization, not container optimization. That's a distinction.
Sure. So when you optimize the container, of course, containers run on nodes. In something like Amazon, they're usually in a scale group. So we also have scale group optimization, and that's probably been covered in other webcasts as well in detail. So when we're looking at the scale group, it may be that the requests are chewing up all the capacity. As you bring the requests down, our analytics will say, now that you've got your CPU requests down, we can recommend a different node type. So we will automatically optimize the node types and the min and max settings on the scale groups as you optimize the node, as you optimize the containers. And that's where the real cost savings come from. Of course, you're paying for the nodes. So if you can reconfigure a node to be a different type or fewer of them, then that's where you start to see the bill go down. So that's all done as one end-to-end analysis of the containers plus the nodes.
Thanks, Andrew. Thanks, everyone, for spending this time with us. And if we can answer any other questions or you'd like to look into trial or a detailed demo, we're here for you. Let us know and we'll get that set up.